Gravity draws dark matter into diffuse halos. Within them, hydrogen gas forms clouds that become more and more dense over time. As gravity compresses the clouds, they begin to heat up, then finally ignite to form the first generation of stars. These stars are giants, much larger than any today. One blows up in a powerful supernova. The model shows an environment transformed by the explosion. The supernova litters its surroundings with heavier elements created in nuclear fusion. Carbon, silicon, iron, and more. These so-called metals cause surrounding clouds of hydrogen to cool. That allows them to collapse. Turbulence breaks them into smaller pockets. A cluster of smaller second-generation stars now begins to form. Here's a wider view of the scene almost 400 million years later. From data generated by the simulation, scientists are working to isolate the dynamics of galaxy evolution. Stars are being born where filaments of gas, shown in blue, come together. Ultraviolet light from these stars begins to strip electrons from hydrogen atoms in a process called ionization. That causes surrounding regions to glow with visible light. The ionized gas appears as bubbles. They're associated with pockets of elevated temperatures, shown in red, as well as high concentrations of metals spread by supernovae, shown in green. The simulation reveals a dynamic that shaped the course of cosmic history. Heating from ionization tends to push the gas out. That suppresses the rate of star birth. Metals, on the other hand, allow pockets of gas to cool and fall inward. That increases the rate of star birth. So instead of stars forming and collapsing immediately into galaxies, the universe becomes a wide mix of hot and cold regions, large and small star clusters, and pockets of gas amid clouds of dust rich in metals. The small dwarf galaxies that astronomers have spotted hovering above the Milky Way are relics of this early period.